Hello everyone and welcome to our calculus notes for section 3.5. Today we're going to be talking about limits at infinity. So we take a break from our derivative stuff here and we're really focusing on helping us to graph any type of function. And the limits at infinity are used to describe the end behavior of a function on an infinite interval. So let's take a look at the graph 3x squared over x squared plus 1. So you can see here that it kind of slopes on down, curves, goes to 0, slopes on back up, and then curves. And this function has a horizontal asymptote at y equals 3. And you can see the dotted line right across there. Okay, so the function will get close to that, but will never reach it. And so we can see the limit here as x approaches negative infinity of our function equals 3. And as the limit as x approaches infinity of our function, it's going to equal 3. And that brings us to the definition of a horizontal asymptote. So the definition of horizontal asymptote says the line y equals L, and L is just a number, and so we know this is a horizontal line, is a horizontal asymptote of the graph of f if the limit as x approaches negative infinity of our function equals some constant L, or the limit as x approaches positive infinity of our function equals some L. So in our first example, it says find the limit as x approaches infinity of f of x equals 3x squared over x squared plus 1. So what we're doing here is we're trying to find the horizontal asymptote. Okay, if it even has any. Okay, and this limit at infinity is going to help us find that. If we want to find this limit, it's going to be the limit of the numerator approaching infinity over the limit of the denominator approaching infinity. So if we think about it, if we plug larger and larger numbers in here for x, this is going to increase without bound. So we really get infinity here. As we approach larger and larger numbers, this is also going to increase without bound. So we get infinity over infinity. But what we were expecting was y equals 3, and we can see here in our graph that it's supposed to equal 3. So why didn't we come up with that? Well, this is what we call an indeterminate form. So limits in indeterminate forms. Indeterminate forms mean that you have not yet determined an answer. When you see something like this, it means, we didn't quite get the answer yet, but an answer still exists. Some other indeterminate forms you might see are like 0 over 0. Okay, so that means we need some other processes to be able to answer this question. So we see this here. If r is a positive rational number and c is any real number, then we know the limit as x approaches infinity of c over x to the r equals 0. Okay? So if we try example 1 again, we're going to try dividing both numerator and denominator by x squared. Okay, so we're going to divide this part by x squared, and we're going to divide this part by x squared. Now, the reason we're doing that is we're trying to get that constant in the numerator. Okay, so if we divide 3x squared by x squared, we do get a constant of 3 in the numerator. And that's what we were trying to do. Now on the bottom, we're still going to have x squared plus 1 over x squared. And so we're going to have to do a little simplification work on this right here. So we still have our 3 in the numerator. Here we can go x squared over x squared is 1, and then 1 over x squared is still 1 over x squared. So if you look at this part right here, this is 1 over x squared. That looks exactly like this. And so we know its limit is going to equal 0. So I guess let me rewrite this with the limit in front. It's easy to get lazy and not put this, but That's what we're looking for, the limit as x approaches infinity. We would get the limit as x approaches infinity of 3 over the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x squared. So we know we can do that with our limits. We just split all that up, and so our final answer here, well, the limit of a constant is just that constant, so it's 3, so the limit of 1 is just 1, and then here the limit as x goes to infinity of 1 over x squared, it's in this form right here, so that's just going to equal 0, and our final answer is just 3. So again, what that tells me is that the horizontal asymptote is at y equals 3. Alright, so that does work, but it becomes a little more tedious to find our answer. So what we want to do now is look at some different guidelines, and we have a little saying, BOBO BOTON EATS DC. Okay, so you can also try to memorize this, BOBO BOTON EATS DC. What we're saying is if the degree of the denominator is greater than the degree of the numerator, then the limit is 0. Okay, and that's our BOBO. Big on bottom equals 0. Okay, big on bottom equals 0. And this is really what we were looking at when we had this right here, c over x to the r. So if this increases without bound and this stays constant, we're going to get a 0 for our limit. Now if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. So this is big on top, n. So big on top equals none, meaning that the limit goes to infinity or negative infinity. So if we were to switch this around, right, and we had something larger on top and our constant on the bottom, this would go to infinity or negative infinity without bound. And the next one, if the degrees of the denominator and the numerator are equal, then the limit is the ratio of the leading coefficients. And that's our EATS DC. And EATS stands for exponents are the same. And then DC means divide coefficients. Okay, so in that case, we would have the same exponents on top and on the bottom, and then it would just be a fraction of their coefficients. Now note, rational functions always approach the same horizontal asymptote to the left and the right. What that means is we don't have to try a negative infinity and an infinity. We could just try the limit at infinity and it's going to be the same. Okay, so let's try our example 1 again by comparing the degrees of the numerator and the denominator and then deciding what to do. So here we have the limit as x approaches infinity of 3x squared over x squared plus 1. So with this rational function, the polynomial on top and the polynomial on bottom, you look at the highest power, the greatest degree here. And in this case, it's 2 and 2. So here, the exponents are the same. EATS DC. Okay, so exponents are the same. What we need to do is divide those coefficients. So the coefficient of this one is 3, and here it's 1. So we know this is going to equal 3 over 1, or 3. And so again, our horizontal asymptote was y equals 3. And so we've found 3 a couple different ways. We found it graphically. Okay, you can see that this is approaching 3. We did this thing where we try to get the numerator to equal a constant. Okay, and we found that it was 3. Or we can use a little shortcut rule where we saw that the exponents were the same, and so we just had to divide the coefficients. Alright, let's give a couple of these a try now. Let's follow these guidelines right here. They're going to save us a lot of time. So if we want to find each of the limits, first just verify that they are rational functions. The exponent here is 1, and here the exponent is 2. So in this case, it is bigger on bottom. So big on bottom 0. So the limit here has to equal 0. Now let's take a look at what that graph would look like. Okay, so here is 2x plus 5 over 3x plus 1. And you can see as we go to infinity that this guy is going to 0 if we go to infinity or negative infinity. So the graph verifies our answer. For the next one, here we have 2x squared plus 5 over 3x squared plus 1. So again, we have a rational function, and if we look here, the exponents are the same. So exponents are the same. So that's eats DC. So exponents are the same. DC is what we need to do. So divide our coefficients of 2 and 3. And so this limit is 2/3. Let's check our graph now. Okay. And you can see as we go to negative infinity that that's sticking real close to 2/3. If we go to positive infinity, you're going to see the same, still staying very close to 2/3. So what that's telling me is my horizontal asymptote is at y equals 2/3. Where was the horizontal asymptote here? It would be y equals 0. All right, and one more example here. Here we have 2x cubed plus 5 over 3x squared. So compare the exponents. In this case, it's bigger on top. So this is our boton. Big on top, n, standing for none. So what this means is we're not going to have any horizontal asymptote. And let's just take a look at the graph and see what's happening there. Aha! So you can see the end behavior here as the top. If the top is bigger, it's going to increase at a greater rate than the bottom and is going to eventually eat it up. And you can see here we don't get a horizontal asymptote. Instead, we have an asymptote that runs diagonally right through here. So anytime it's bigger on top, you are going to get this type of asymptote right here. But today, we're really concerned with horizontal asymptotes.